Projectiles, Part 2. Here are your priming questions. What I want to start with is looking at these vectors, the x's and the y's separately, and then thinking about them together. And here is where I also want to talk about a couple of shortcuts and things to keep in mind for your projectile problems. The first thing I want to remind you of is the horizontal velocity. So if you look at the horizontal velocities here, the horizontal velocities all remain constant. So this goes back to what we said before. When it's in the air, only gravity is working on it. In the vertical, so the horizontal remains the same in terms of its velocities. Now, the other thing I want to mention is if you look at the vertical velocities when they are at the same heights, the magnitudes are all the same, just the directions are different. So if we have an object that is from the ground level or from any similar heights, we know that the vertical velocities will have the same magnitude, but the opposite direction. The other thing I want to mention is at the very top, what you'll notice is that it only has a horizontal velocity. It has no vertical component because at the peak, that is where its vertical direction is changing. And anytime you have a change in your vertical direction or in any direction, at a moment, you're going to have a zero velocity in that particular direction. So here we have a vertical velocity, and then no vertical velocity. So at the top of the trajectory for a projectile, we know that the vertical velocity is 0. And that's going to help us define the height or the highest point that the object is able to go. So let's talk a little bit more about our conceptual ideas. So we have non-horizontal projectiles now. What this means is that our initial velocity is non-perpendicular, shown by this vector, which means in order for us to do our calculations, we need to split it up into its x and y components, and this will be the x, and this will be the y, and our x component for the velocity is going to remain constant throughout the problem. That'll be our v average, our vf, and our v naught. Whereas this vertical component will change over time, and this will be our v naught and our y, so v naught y. And if we were to imagine this as a projectile, this would be its displacement, something like that. And we could measure the slopes if we were to plot this out on a graph, and we could figure out what the velocities were, and that would be the combined x and y, whatever the y component would change to, and that would be our velocity at any point along this trajectory. So as a reminder, you need to split that initial velocity into the x and y components. You'll need the angle, and then you'll need to use sine and cosine in order to figure out your x and your y components. X stays constant, y will change due to the acceleration of gravity. So let's do a practice problem. In this, we have Leonidas throws a spear with an initial velocity of 23 meters per second from ground level at 65 degrees north of west towards the ornate head of Xerxes. Luckily for Ringface, the spear missed him by a hair and continued on his trajectory unimpeded. Calculate the hang time, the final velocity, the peak height, and the range of Leonidas' spear. So if you were to imagine this, initially this would go up, misses, and then it comes back down to the same height that it was thrown at. So in this case, actually let's get to our x and y axes. And that should be an x. All right, so what do we know first? We are told the initial velocity and the angle. And so what we want to do is we want to draw out our vector. In this case, it is a non-perpendicular vector. So that means we're going to have an x component and a y component. And that should be straight up and down. Like that. All right. We know that this value for the non-perpendicular is 23 meters per second. And we know we are measuring from west going north by 65 degrees. So this is the angle we have here. That is 65 degrees. And now for the x component, we know that that is going to be the adjacent. So we use cosine. So that is going to be 23 cosine of 65, which gives us an x component of about 9.72 meters per second. You'll notice that right now I'm not using significant digits because when we do our final answer, that's when I will use my significant digits. So this is going to be the x component. So that's going to be my velocity in the x is 9.72 meters per second. And now for the y, I'm going to use the opposite end hypotenuse. So I'm going to use sine. So this will be 23 sine of 65, which gives me a y component of about 20.85. And so this will go in the y. And what I want to do now actually is I want to go ahead and group all this together and put it off to the side. And so now for my y, I know that my initial velocity is 20.85 meters per second. Now, from here, we can start listing our other variables. We know that this initial velocity is going up, so we have set up as our positive. So when we talk about the acceleration due to gravity in the y, it now must be negative 9.8 meters per second squared because it's going down. And if we are first looking for the hang time, this will be for the entire trajectory as it goes from the ground back to the ground. Since it's going from the ground to the ground, we know that our vertical displacement is 0. And not only that, because we are ignoring air resistance, from the shortcut that we talked about before, we know that our final velocity in the y is going to be the exact same magnitude but opposite direction. So that means it's going to be a negative 20.85 meters per second. It's going down at that speed. And so now what we need to look for is the hang time. We have our V naught, we have our A, we have our D. Oh, and our D, that should be just meters, not meters per second. There we go. And so we have our V naught, A, D, VF, and we're looking for our time. And we can just use VF is equal to V naught plus A T. And we have negative 20.85 is equal to 20.85 plus negative 9.8 times time. And when you work this out, you should get time is equal to 4.3 seconds. So we now have our time. We can, this is actually 4.3 seconds. And we can go and put that in our x-axis as well, because remember the time is here, so time is equal to 4.3 seconds. So now we have the hang time. We need to find the final velocity. And for this, it's actually easier than we might think at first. In this case, we have our final y velocity is negative 20.85. Our x velocity, again, hasn't changed. And what we've noticed here is that our VF and our V naught have the same magnitude. And so when you draw out your final triangle, this is going to be going down and then going to west. We already know that this is going to be 20.85. And I'm not using the negative here because I'm already showing the direction using the vector here. And this is 9.72. And this triangle should look familiar to us because it looks almost exactly the same here. So we know that this is going to be 23 meters per second. And we can even utilize the same degree markings there. So if we were to do that but transpose it down, I can show you the triangle like this. Remember, it's going to be the same. And then the angle here will also be 65 degrees. So we would be able to write this out as 23 meters per second at 65 degrees. This would be south of west. That would be our final velocity. And again, this matches the shortcut that what we were talking about before. So that's our final velocity. Now for peak height, we have to change some of our variables here. And in this case, let's go and relist these variables out. So we have our y. We know that we have a initial velocity of 20.85 meters per second, and that's going up. We know our acceleration is negative 9.8 meters per second squared. Now here's where we have to be careful. We cannot use this time directly. In fact, we don't even need to use this time, but you can if you want. This time was for the entire part of the trajectory from going from the ground to the ground. But that's not what we are looking for now. What we are looking for is the peak height. In that case, we could use half of the time if we wanted to, but we actually don't have to. We can use our other shortcut to make things easier. We know that our final velocity in the vertical at the peak is going to be 0 meters per second. And if we're looking for the peak height, that means that we are looking for our vertical displacement like this. And so in this case, we don't even need the time. We could use it if we wanted to, but we don't have to, because we have an equation that relates all these four variables together. So we have VF squared is equal to V naught squared plus 2AD. And we know our VF is 0. So 0 squared is equals 0. And that's going to be equal to 20.85 squared plus 2 times negative 9.8 times d. And remember, we have to be careful of our directions with our acceleration here. So when you work this out, you should get a peak height displacement of 22 meters. Check your work to make sure you're able to get the same answer. And this is going to be 22 meters up. That's going to be the y displacement for the peak height. And for the last one, we're looking for the range. And again, for the range, we need to use our x. And we can think back to our basic equation for the x, where we have v is equal to displacement over time. We have the total time, which is what we need for the range. We have our x velocity, so we can find our range, which is our horizontal displacement. So we have 9.72 is equal to d over 4.3 seconds. When you work this out, you should get a displacement in the x. I'll go and do an x subscript of 42 meters. And this is going to be going west. And there you go. If you have questions, we'll address them in class. And here are your priming questions again.